As promised, this whole entire thing's going to be about some mindless calculating. I have a couple of resource guides that are hopefully available under the appropriate section of Canvas. And we're going to be pretty much doing three different things today. The first thing we're going to talk about is we're going to talk about a concept known as reaction quotient, right, which is represented with a Q, not to be confused with equilibrium constant, which all very confusing, but we'll see that kind of in part one. Part two, we'll go into some actual calculating. And then in part three, we're going to see what's called a Hess's law type calculation. And this is where we're going to be using some of the, I guess, the Keq manipulations that we saw kind of towards the end of the last video lecture. So stick with me. So probably it'd be a good idea to start off with just a kind of typical example. And so keep in mind, everything that we see this week is going to have to do with this idea of a dynamic equilibrium, right? Where any equilibrium process reaches this point where the forward reaction equals the rate of the reverse reaction. And we talked about the fact that we could end up with that position of equilibrium more towards products. And we also said that there could be a position of equilibrium that is more towards reactants, right? It doesn't mean that it's automatically a 50-50 mix of these things. In fact, it can establish itself anywhere along that continuum. And as a part of kind of talking about that is we talked about this, this numerical value called Keq, right? Which is the equilibrium constant, right? And so let's write that down. So this equilibrium constant could be expressed in terms of concentrations. That would be considered what's called a K sub C, and it could also be in terms of partial pressures if you have a system that is just gas, and obviously this one is just gas. So we could very easily measure an equilibrium constant for either one of these values. These are both, by the way, considered KEQs, not to confuse you. And of course, there are ways of like converting one number into another, but we're not going to bother with that in this class. That's more a Gen Chem type concept. So the equilibrium constant, right? Keep in mind that it always has the same structure, right? It always is the products divided by the reactants, where if, let's say, we have this Kc that we're looking for in terms of Keq, we're going to do it in terms of concentration. So let's just turn this guy into the Kc expression. So maybe we'll just do, Keq or Kc or however you want to express that. The first step is to recognize that the only thing that we're going to involve is anything where the concentration can change. So those are things that gases, like aqueous phases. We would not include anything in this thing that is either a pure liquid or a pure solid, right? And that's kind of a bizarre thing about Ks that, we may occasionally encounter here. So we are going to do the concentration of the products and divide that by the concentration of the reactants. And notice that this particular reactant has a 2 in front of it, right? That 2 coefficient, that coefficient is going to square the concentration in the equilibrium constant expression, right? And so if I wanted to ask a question, as you'll see in your resource guides, about the equilibrium constant expression, it is requesting you to draw this, right? That is the expression, right? The value of that, which we're not going to calculate because, quite frankly, I don't have the equilibrium values in front of me, would be where the number that we ended up with if we plugged in those molar concentrations in each case. But the expression itself is just this. So notice that these concentrations right here, I'm not going to put it because it would get a little messy, should really say equilibrium, right? It should be like a little sub-EQ down there because these are experimentally determined values, right? You let an equilibrium establish itself, you measure the concentrations of all those things. And if this thing was very far towards products, right, we would end up with a very high concentration of these things relative to those things, and Keq would be much, much greater than 1. If this thing was more towards reactants, then it would be some fraction of 1. If you don't remember that, make sure you watch the previous video lecture, and there's a little bit of a discussion about that. What we're going to be talking about today, this equilibrium constant, is commonly confused with, but is very different from, something called the reaction quotient, right? And so let's draw the reaction quotient up here, and I'll kind of compare the two. Okay, it's already getting pretty messy and confusing, so bear with me here. What this equilibrium quotient is abbreviated with a Q, right? Notice that Keq is not the same thing as Q. The confusing thing is that this equilibrium quotient, whatever the heck it is, apparently has the same exact form as the equilibrium constant. But what is different about these two things, and this confused me for the longest time, is that these are concentrations I have a control over, right? So in other words, if I were a chemist, I could take my reaction flask and I could throw in a certain molarity of all of these things, right? And I could calculate that, and that would be an equilibrium quotient that I was calculating, right? And then what you would do is you'd compare that Q, the size of Q, to the size of Keq, right? And Keq is not something that I, as a chemist, have control over, right? That is nature's job, right? These equilibrium concentrations are something that, nature kind of dictates to me, right? Anytime you see this Q value or quotient, that is something that the experimenter is actually putting in a flask, right? And so what you can do is you could compare the size of Q to Keq in order to determine which direction the reaction goes. So let me write down a little bit of a chart to make this a little bit easier. So let's pretend I went through all the calculations required to determine a Keq, right? And that Keq was 160, right? And well, what you would say is, well, it looks like this process is a little bit towards products, right? Because it's greater than 1. But it's still in that region where we're still going to call it an equilibrium process. It's certainly not a complete reaction. And so what I could do is I could say, okay, I'm going to go into lab and I'm going to measure an exact amount of all 4 of these things out, and I'm just going to dump it into the reaction flask and then take my hands off and ask, which direction does that reaction go, given the fact that I know my Keq is this? Well, there's a couple of different possibilities, right? Q could be bigger than Keq, right? And so let's just pretend, so in this case, for example, let's say that I put everything in, and let's say that my Q was, I don't know, 1,000, right? So I plug all those values in, and I recognize, whoa, Q is much bigger than Keq. Well, what does that mean? It means that there's too much product there, right? There is just way too much product. So what would happen in a case where Q was greater than Keq is you would overall see this reaction go to the left in order to establish equilibrium, right? It's trying to get rid of products, right? Remember, this is products over reactants in both cases. So if you have a number that is too high in your Q, you're going to try to make that lower by decreasing the amount of products and increasing the amount of reactants, right? And so let's put over here, so moves towards reactants. Okay. Well, obviously, if the other case was true, if I threw a bunch of stuff in there and Q ended up less than that experimentally determined value, let's say that, I don't know, my Q was 10 or something, right? Well, that would mean that I didn't have enough products and I had way too many reactants. And so what we would see in a case like that is a shift to the right, right? And that is, of course, an example of where we would move towards products. And if you remember the very beginning of the last video lecture, I said I was a big fat liar, right? Well, I wasn't necessarily a big fat liar, because what we were talking about in every case was some place where I didn't have any products around. I knew that there was a whole bunch of reactants there, right? And so by necessity, right, Q is 0 in that case. So of course, even if it was an equilibrium process, it would still go in the forward direction, right? The part that I was still lying to you about is this idea that it would just keep going towards products forever. Some reactions do that. There are reactions that definitely don't, right? So you may recognize I didn't talk about, well, what if Q is equal to Keq? Well, friggin' that means it's already at equilibrium, so you would fill it with all of that stuff, take your hands off, and not a damn thing would happen, or at least to your eyes, not a damn thing would happen, but we now know that a whole bunch of stuff is actually going on. So that's how we're gonna use Q. We'll see this over the next couple of weeks here, and certainly in today's discussion, that'll become important. Right? So try your best not to be confused by those two things. I don't know why we named them so similarly. It is really confusing. So I really do think, Q, I have control out of, right? That's something where I'm physically doing something. Keq, that's something where the universe kind of tells me what it is, okay? So we'll do some specific examples of that. Okay, if all is going according to plan, you should see a little screenshot of one of the resource guides, and it should involve a set of questions that involves this equilibrium. I've got it right over here in the corner. It says, write the equilibrium equation, which by the way is the same thing as the equilibrium expression, in the forward reaction, right? So in other words, I need to do my balancing step, and then I'm going to write out the structure of that expression. So you'll notice here that I've got something that's imbalanced, right? I've got too many H's. So first step for a lot of these is going to have me balance this sucker out with my coefficients. I've got 4 hydrogens and 4 hydrogens, and over on this side I now have 4 oxygens. Right? So we're going to put a 2 in front of the oxygen. Now I'm going to be able to answer question 1 here. Well, in the forward direction, Kc, we'll just do Kc, we could do Kp as well, since they're all gases. We're going to put the products concentration, right, where I recognize that there's a 2 in front of water, so I got to square that concentration all over those quantities, right? So that hopefully will make a lot of sense. Later on in the question here, it says, what is the equilibrium constant if they have a whole list of values? So let's go ahead and just plug those in right now. Okay, so here I have the equilibrium constant all written out. And now they're asking me to actually calculate its value based on some experimentally determined values. I just did a whole section of this video where I used the wrong numbers. Now I have to go back and do it all over again. That feels really good. So let's make sure I use the right numbers this time. So I've got 0.45 for my concentration of silicon tetrahydride. I've got 0.25 for my O2 concentration. I've got 0.15 for my SiO2, and I've got 0.10 for H2O. So now let me plug these correct values in and see what I end up with. Okay, so I've got a pretty small number, 0.053. Keep in mind what that Keq is telling me is that this reaction as written is actually pretty far towards reactants, right? And so there's just a kind of a rat's fart of products floating around out there. And so let's take a look at question number 2, which asks about, first of all, the expression for this thing going in the opposite direction. And then it also asks for the value of the equilibrium constant in the reverse direction. Okay, so keep in mind, based on the last set of video lectures, that anytime you're asked about the value or the expression in the reverse direction, you simply take the reciprocal of whatever your original expression was. So I'm going to take Kc and put it in reciprocal form, which is just a fancy way of saying that what used to be in the denominator is now going to be in the numerator and vice versa. Okay? And then we look down at the questions and it says, what is the actual value in the reverse direction? Well, I could go through the pain and suffering of plugging everything in again, or I could simply take that value that I calculated in the first step and take its reciprocal, right? So we're going to take the original Kc and take its reciprocal, raise it to the -1 power, and we end up with just about 19, right? That should make sense because keep in mind, as it was originally written, I ended up with a whole bunch of reactants. So now if I'm talking about the reverse reaction, and those things would become the products, right? So they should be present in a greater extent. So now let's go to an actual equilibrium quotient calculation. So keep in mind, equilibrium quotient has the exact same form. It's just that now I'm providing the reactants and products and trying to figure out which direction the reaction goes. So assuming I could write these down correctly. So we have a numerical value for the reaction quotient. And keep in mind, the only value of these Q's is in comparison with whatever the actual Keq is. So I look at this number and I can tell that it is much bigger than 0.53. What that means, therefore, is that I have too many products, so this is going to actually move in the direction of reactants now. So I'll just say, therefore, moves towards reactants, or in the reverse direction. Right, so that's a great example of the way that we can use Q's to determine which direction a reaction will go in this crazy new world we live in. This last little bit is just pure manipulation of KEQs. We don't have to worry about reaction quotients at all for this one. If you take a look at the screenshot, there is a resource guide that I've provided. And the key to these kinds of problems is to recognize that you can actually determine quite a bit about the equilibrium of some expression that you've never even performed just by being able to add together reactions and manipulating equilibrium constants. So this is how it works. An important thing in these problems is to keep in mind what the goal is, right? And so the equilibrium that I care about is this one, and then I'm going to try to calculate a Kc based on the given information. So what you'll see is on that resource guide, you're going to see information about Kc's for 2 different processes. I'm going to try to keep it to just 2 because 3 becomes a little overwhelming. And what you'll notice is that each one of these reactants or products is involved in the previous 2 equations, right? So let's take a look at this very first one that's written on your page. The fact that HF is in an acid-base equilibrium, or I should say a dissociative equilibrium. And I'm not worrying about phases, right? These are all aqueous. And it gives me information about the Kc of this. Okay, so the idea is I am going to add up the 2 provided equations, and I'm going to use that addition to kind of tell me what to do with these Kc's. So the first thing I notice is that I've got 2 F minuses over here, and I've got 2 HFs here, and I don't really know what the heck's going on with this at this point. So what I'm going to do is, just to make sure I have the right amount, I'm going to take and multiply through by 2 every single one of these things. And I know if I multiply by 2, in Kc world, that is the same thing as saying I need to square whatever that Kc is. So that's what I'm going to do. And then I look at the very next reaction, and I'll notice that the reactant in there is actually kind of on the wrong side, right? I notice also that this C2O4 2- is on the wrong side. So I'm going to reverse this reaction as written. And we already know that if we reverse an equilibrium, notice that that is the exact opposite of what's written on your page. I went through and I actually took that equilibrium constant and took the reciprocal, right? And so I've got 2 bits of information. You'll notice that when I go through and try to kind of add both sides together, these H pluses go away, and what I end up with is all of the proper things on the left side, all of the proper things on the right side. Now, how do I figure out Kc? Well, it turns out that if I'm going to add these 2 reactions together in order to get to that particular equation, I have to multiply the Kc's, right? And so I am going to multiply that Kc information. So here you can see that I've now multiplied these things together. Let's plug that into our calculator and see what it ends up with. And what I ended up with was a pretty small equilibrium constant. So check my math. Hopefully that works out. We will see this on the homework. Bye-bye.